Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at finding volumes using the shell method. In the previous videos we've looked at the disk method and the washer method for finding volumes, but they're not always going to be the best or even possible to find volumes. So we're going to look at another method called the shell method. And if we take a look at an arbitrary area with f of x as the top function, g of x the bottom function, and if we bound it by x equals a and x equals b, what I want to do is take a look at how we could find the volume of this area if it was rotated around the y-axis using vertical rectangles. So when these rotate around the y-axis, it does not form a disk, it does not form a washer, it forms a shell. Here's our y-axis, here's our representative rectangle, and it's going to go around the y-axis. So when it does that, it creates what's called a shell. It's like an open tube. And we can find the volume of this shell. If we were to take a shell and cut it open and lay it flat, and we want to know the volume of the material used to make that shell, we could do so by basically taking the length of this side, the width of this side, multiplied by the thickness. But when it's rolled up into a shell, this length here will be the circumference, and this length here will be the height of the shell, and then we have the thickness. So hopefully you can see that. Therefore, in order to find the volume of a shell, we find the circumference, this length around the circle. So that's 2 pi times the radius. That gives the length of that rectangle when we roll it out. Then times the height. So far we've just got the 2 dimensions, and then we need to multiply by the thickness. And I'm just going to write thickness instead of writing another variable. That's how we would find the volume of that shell, whether it was a paper or cardboard, or the shell that's formed by that rotating rectangle. So now let's express that in terms of our functions so that we know how to find the volume of a shell formed by rotating this representative rectangle around the y-axis. So if 2 pi is a constant, we can leave that out front. And we're going to be adding up all of these slivers or representative rectangles from a to b. So we use integration to do that. So the integral from a to b. Then we need the radius of the shell. So the radius is the distance from the axis to this rectangle. So that value is going to be x. Then the height of that representative rectangle will be f of x minus g of x. And then the thickness of the shell that's formed will be dx. So this formula will allow us to find the volume of a solid that's formed when we take an area, rotate it around the y-axis, and we use vertical rectangles. And what I want to point out here is in using the shell method, your representative rectangles have to be parallel to the axis of revolution. Let's take a look at using this in some examples that we've done previously. We did this question in the last video. It says find the volume of revolution generated by revolving the area enclosed by y equals 1/2 x squared, x equals 4, and the x-axis around the y-axis. So we draw that region. So the area bounded by y equals 1/2 x squared, x equals 4, and the x-axis. So this is our region. And it's revolving about the y-axis. So the way that we did it in the last video is we had to work with horizontal rectangles, and then they became washers as we rotated around the y-axis. This time we're going to work with vertical rectangles. Because it's a parallel rectangle to the axes of rotation, I am using the shell method. It's nice using vertical rectangles because our functions are already in terms of x, and we know our boundaries in terms of x. We've got 0 and 4. So we're going to plug into our formula. From 0 to 4, x times f of x, that would be the top curve. We want to describe the length of this representative rectangle. So it would be the top curve, which is 1/2 x squared, minus the bottom curve in this case is y equals 0, so it's just a 0 dx. Now we're going to simplify. So we're going to have 1/2 x cubed dx. And this is a much easier integral than the way we did it in the previous video. You can do it either way, you'll get the same result, but I'm just giving you another option. And when we integrate this, we're going to get 1/8 x to the 4th. And that simplifies. Before we start, 2 times 1/8 is 1/4 times pi. So that will equal 1/4 pi times 4 to the 4th power. One of the 4's will cancel, so I'll end up with 4 cubed times pi, which is 64 pi cubic units. That's the same answer we got in the previous video, and I think less work. Let's take a look at some more examples. Find the volume of revolution generated by revolving the area enclosed by y equals x squared and y equals 4x around the y-axis. So we're going to draw our curves. So this is the region that we want to rotate around the y-axis. And we need to find our points of intersection, which we've done before. So our x values are 0 and 4. We're going to work with a vertical rectangle and rotate that around the y-axis. So let's plug into our formula for the shell. And I know I'm using the shell method because my representative rectangle, which is a vertical one, which means I'm doing everything in terms of x, is parallel to the axes of rotation. 0 and 4, x times f of x, the top curve, is 4x, minus the bottom curve is x squared dx. So again, we need to simplify before we can integrate. Now I can integrate. So we'll get 2 pi times 4/3 x cubed minus 1/4 x to the 4th. I evaluated at 4, and when I evaluated at 0, it's just 0, so I just need to evaluate it at 4. So when I evaluate that, I get 256 over 3 minus 64. Get a common denominator, combine those fractions, and my final result will be 128 pi over 3 cubic units, which I can leave it like that or write it as a decimal value. Let's do one more example. In our next example, it says find the volume of revolution generated by revolving the area enclosed by y equals 5x cubed minus x to the 4th and the x-axis around the y-axis. So we're rotating around the y-axis. This isn't one of our basic curves, so I've actually drawn it in the interval that we're interested in. So it actually intersects the x-axis at these 2 points at 0, and we'll find this other point. And this is the area that we're talking about. It's not possible to define a horizontal rectangle because this function is the same as this. So if you subtract that, you're going to get 0. So in this particular example, we do need to use vertical rectangles. And because it's parallel to the axes of revolution, we're using the shell method. Let's find our points of intersection. Points of intersection will be when this function is equal to 0. Factor out an x cubed. So x equals 0, we already know, and 5 minus x equals 0, in which case x equals 5. So those are our limits on our integral. Now we can find our volume using the shell method. The volume will be equal to 2 pi times the integral from 0 to 5 of x, okay, that's the radius of the shell that's formed when this thing rotates around, times the height of that rectangle. The height will just simply be this function, which is 5x cubed minus x to the 4th, times the thickness of that shell, which is dx. So we'll simplify. And then we'll integrate. So we're going to have x to the 5th minus 1/6 x to the 6th. Now we're going to evaluate. When we put a 0 in, makes it easy for us. 5 to the 5th power is 3,125. 5 to the 6th power is 15,625 over 6. Get a common denominator, subtract, and then we can cancel a 2 there. So our final answer will be 3,125 pi over 3 cubic units. Practice some of these, and then in the next video we're going to look at using the shell method when we're working with horizontal rectangles rotating about the x-axis. Take care and see you later.